basic for understanding phaco-dynamics. You heard, I'm going to skip through some of the old slides in the talk because you heard this morning about some basics of how the phaco-emulsifier operates. Financial disclosures. My colleagues and I were on the way to the Vietnamese National Institute of Ophthalmology in Hanoi to meet with my friend Dr. Động, head of the cornea service there, and Abbott is paid for our detour to come to this meeting here. So there's a challenge to there are multiple challenges to the phaco surgery. You have to balance the power of the intensity of the phaco, which pushes fragments, nuclear fragments away, with aspiration flow rate, which attracts nuclear fragments to the phaco needle, and vacuum, which holds nuclear fragments to the phaco needle. So what's the logic of our phaco-emulsifier settings? How do we get this done? This is a diagram of a phaco-emulsifier. This was explained to you this morning with irrigating bottom, irrigating through the phaco needle into the anterior chamber with an aspiration line that's controlled by a pump. Phaco power is generally thought to be a function of the stroke length of the needle, how far you have excursion. However, we now have advanced functions of these phaco needles. From Alcon, we have Basel, which essentially rotates the needle and requires a bent needle, because if you just rotated a straight needle, it would just core an apple. So for the shearing effect, the needle has to be bent. From Abbott, we have the ellipse function, which is like a three-dimensional hair shape or egg shape function of the phaco needle. So it moves in and out, and also has this elliptical three-dimensional function for shearing. You can use this with a straight needle, or you can use this function with a bent needle. It doesn't matter. I think that if you're going to go to advanced techniques like chopping, that a straight needle is a whole lot easier to use. We have a peristaltic pump that was explained to you. This is simply most machines is a rotating pump. And we have a foot pedal, which has essentially 3 positions when you're in the phaco mode and 2 positions when you're in the irrigation aspiration mode. So how is intraocular, first concept is how is intraocular pressure controlled? Intraocular pressure is controlled by the bottle height. So if you have a pinch valve open and you have no pump flow, you have about, and the bottle height is at 45 centimeters of height. That's equal to about 6 inches of water, 15 centimeters, 11 millimeters of mercury, so 45 centimeters of height is going to be an intraocular pressure of about 30 millimeters of mercury. Now this obviously changes during your procedure. How does it change? What do you do to make it change? So when you start the pump flowing, what you're actually doing is reducing the intraocular pressure in the anterior chamber. So any kind of pump flow reduces the intraocular pressure in the anterior chamber. How does flow affect the pressure in the aspiration line? Flow creates a differential pressure between the intraocular pressure in the anterior chamber and the aspiration line, such that if you have a high pump rate, you're going to have a bigger differential between the pressure in the anterior chamber and the pressure in the aspiration line. This doesn't necessarily mean that the pressure in the aspiration line is going to be negative below atmospheric pressure. It does not. It just means that you have this differential. Slower pump rate, less of a differential. Still can be positive in both places. So what does this mean for you as a phaco surgeon? If you have a low flow rate, then you're going to have a positive pressure in both the anterior chamber and in the aspiration flow line. It'll be lower, but your differential will be less, but it won't be positive. So when is there no flow into the anterior chamber? With the pinch valve open, obviously there's no flow when you get occlusion of the phaco needle. Okay, then there's no flow into the anterior chamber. Or you can have the pinch valve closed. If the pinch valve is closed, then your anterior chamber is going to collapse and you're going to have an intraocular pressure of 0. The total occlusion, you're going to have intraocular pressure in the anterior chamber. That's going to be equivalent to your body count. So what are some of the logic of the machine settings? What can you set as a surgeon? You can set the bottom height, you can set the ultrasound power, you can set the vacuum that you will attain if you totally occlude the phaco needle. It'll never be attained if you don't totally occlude the phaco needle. And you have the aspiration flow rate, which you can set in cc's per minute. So all of this that I'm talking about is not my stuff. It's described in Dr. Snipell's excellent book called Phaco-Dynamics. I highly recommend it to understand the logic of machine settings, and even for advanced techniques. Okay, so why is all of this important? For you, again, as a phacosurgeon, it's important for two major reasons. Followability, you want to get the nuclear fragments to your phaco needle, so you can use phaco power to fragment it and aspirate it. And for surge, two things you have to worry about. The flow pump directly controls the aspiration flow rate, and as we're going to see, it indirectly controls the intraocular pressure in the anterior chamber and the vacuum level in the aspiration flow. So, what happens if you have occlusion? If you have a partial occlusion, here, if you have partial occlusion, then the intraocular pressure goes down. If you have total occlusion, then the intraocular pressure, as you see down here, goes back up to what is determined by the bottom line. And what we're actually doing is alternating between partial occlusion and total occlusion of the phaco needle, as we're going to see. So you have two issues when you want to emulsify. You have what's known as distal followability. You want to bring the peripheral, you've already divided the compartment, you split it apart. Now you want to bring the pieces to the phaco needle. That's based on distal followability, which is based on the aspiration flow rate. If you're having difficulty bringing the nuclear fragments to the center of the pupil for emulsification, you can increase the flow rate. Or you can bring the aspiration port closer to the fragment that you're trying to bring to the center to emulsify. Those are your two choices. Then you have proximal followability. What's proximal followability? Proximal followability is when you have partial occlusion of the phaco needle. And that's really mostly controlled by vacuum. Partial occlusion increases the resistance in your aspiration flow line, and you start getting some vacuum that goes up towards your preset level. Now, why is this important? Because I'm going to show you a short video. What we're really doing to get out nuclear fragments is called partial occlusion phaco, or carouseling phaco, which is what Dr. Secker calls it in his book. And so this is what you're doing. You, in foot position 2, in the top image, you've occluded your phaco. Then you go to foot position 3, and you have some phaco power, and now you've fragmented the nuclear piece that was occluding the phaco needle. So your ultrasound cycle is on, and now you break down the fragment, and now you have partial occlusion. Then flow and vacuum take over and aspirate the particles that you've created. And as you can see on the green arrow, because you have partial occlusion and you have aspiration going on, the fragment actually carousels into your phaco needle to start the cycle over again. So that's actually what you're doing. You're doing proximal followability with partial occlusion or carouseling phaco. You have to, in doing this, you have to pay attention to the interchamber currents. If you increase your flow, you're going to have increased leakage to your incision. If you increase the flow, you're going to have decreased safety because increased flow is going to have a tendency to bring iris and any flap of capsule that you have into your Phaco needle, which you don't want. So you have to balance safety with your aspiration flow rate. Surge is the fundamental limiting factor for high vacuum and the aspiration flow rate. What's surge? You have a Phaco needle that's occluded, you have high vacuum at a preset level. In your aspiration flow line collapses, physically collapses. Then all of a sudden, you're doing closed-cell and Phaco, and you go into foot position 3, and you get this emulsing, and you break occlusion. You have partial occlusion at this point. So what happens? The aspiration line expands, and you get this increased inflow of fluid into the anterior chamber. When the vacuum and ultrasound break occlusion, you'll have sudden increased vacuum in the anterior chamber, and the anterior chamber can collapse. So the fundamental concept of preventing surge when you're doing partial occlusion Phaco is to raise the bottom level. That's the first thing that you do. You start seeing the anterior chamber collapse. The second thing you can do is to lower the vacuum. So you have to be well aware of the principles of fluidic balance. The aspiration flow rate is the relevant parameter when aspiration port is not included. Vacuum is the relevant parameter with complete occlusion of the port. With carousel and Phaco, flow and vacuum work together to enhance followability. And always optimize technique before turning to technology or blaming technology. It's not the machine's fault. Okay, so let me show you a short video demonstrating some of these principles. So this is one of my residents doing Phaco, and initially there's the hydrodissection and the hydrodelineation. But what I want to show you, first we clean out on the surface of the lens the pockets so that you don't get an excision burn. You clean out some of the OVD, and you clean out the cortex and the epinucleus down to the nucleus. This is how we teach Phaco. And then he's splitting his first groove. And remember, this is resident in training. This is how we teach them. Cracking the nucleus. And now, watch the foot pedal icon. He's in the ellipse. Did you see how he used foot position 2 to bring the piece, the fragment, to the center? And then watch it carousel. See, foot position 2, not foot position 3. No Phaco peripheral. Watch it again. Foot position 2, using distal followability, and then carouseling, going into foot position 3, and using partial occlusion Phaco. Okay, that's what's safe. Again, foot position 2, just with aspiration, no Phaco power. And then going into 3 and watching the carousel like we talked about. Now we're going into the epinucleus function. We'll talk about this in the next lecture a little bit. Bringing, again, using followability to shave the rim of the epinucleus, and eventually, watch, he's only in foot position 2. Getting the epinucleus, rotating it, and only in foot position 2, using no Phaco, very safe, and having it trimmed so that it then flips, all with control, with no Phaco power at all, using the principles of followability, distal and proximal followability. Using Dr. Seibel's second instrument, holding it there so that the cluster capsule does not come off. This is a resident that maybe 20 cases. Okay. So now let's move on to the next lecture. We'll talk specifically about machine settings.